Hello. In this video, we'll learn about thermal deformations and the cases when they start generating internal forces and stresses in the members and structures. So we all know from basic physics what is the impact of temperature on metals. They expand, they contract if temperatures increase or decrease. So if we show here kind of a member with length L and it's subjected to a difference in temperature of delta T, and this delta T is positive, meaning that it's an increase in temperature, that results in an expansion of the member by delta temperature. And this delta temperature is a very simple formula to calculate. It's alpha delta T L. And alpha is called coefficient of thermal expansion. Delta T is the temperature change amount, positive if it is increase or negative decrease. And then the member original length is L. Just something to pay attention to, the units. So delta is a length unit, like an inch. The length is also an inch. Let's say if we give an example, delta T is degree Fahrenheit, if you are in the US. So this leaves us with that alpha is equal to the inverse of degree Fahrenheit. So just something to pay attention to when you deal with the units. So now, so far, the member is just free to elongate with temperature increase or contract or shrink when temperature decreases. So if we're thinking about strength of materials, we actually don't have any job to deal with here. It's just calculating the deformation and that's it. The problem happens when there is a constraint preventing this member from relieving due to the temperature by expanding or contracting. So there's a constraint holding them from doing that. And in this case, stresses and internal forces will start developing. So let's explain that by this example. So we have the kind of the same member, similar, we just put it vertical, and now we constrained it by two supports. So the vertical at A and B. I have now a temperature change of delta T equal to positive 75. The area is 3 inches. Alpha is this value. You can see the inverse of degree Fahrenheit. And E, the Young's modulus, is the Young's modulus of steel. So 30 mega pascal, mega psi. So how to, we know now it's constrained, so it wants to expand, but it can because A and B are the points are fixed. So there should be some forces developing internally, and reactions at A and B start to develop here. So we need to find the internal stress due to delta T. So how to do that? We'll use the redundant force method because this is a statically indeterminate member. So I need to look at what is a redundant support here to remove it just temporarily as one case to analyze that member, and then look at a second case where I will reflect whatever redundant reaction I took out. I will put it back, and adding these two cases will give me back the original case. So the original case has that length of the 3 feet member constraint at A and B with the load, if you think about it, the thermal load here, delta T. So now that will result in reactions at A and B, FA and FB, and I will call them different notations, but they actually are equal to each other if you do the sum of forces in Y. Now I will kind of make a copy of that bar, but now remove one of the redundant, I will remove the redundant reactions or support that is not needed actually for stability reasons. So I will decide to remove the one at B. This is something I will fix quickly here. So this is not 3, this is B. Now one of the bars that's now statically determinate, I will put on it the loads I have, which is the delta T thermal loading. And then on the other one, I will not put the loads, and we'll see what we're going to put here. But under delta T, you will have the member now freely expanding delta, the deformation T now, if I call it. And then for the other bar, I will put back the reaction that I removed, the redundant reaction that was not needed, which is FB. And that will cause contraction, compression in the member. And the idea here that in the original system, the deformation between A and B, these two fixed points, is equal to 0. So delta, which now if I look at the two cases I have, the deformation information that I will add from the case 1 and case 2, delta T and delta F, they should add up to the original deformation I had in the original case, which is now is equal to 0. So delta temperature is equal to alpha delta TL, and delta force is equal to PL over AE. Plug in all the values I have, and you find that you are only missing here FB, the reaction, the redundant reaction that was removed. And if I solve for that, I'll find that FB is equal to negative 43.9. Negative makes sense because now that means that this bar is under compression. And it complies with the understanding here of the behavior. So if FB is equal to negative 43.9, then I can plug this in to figure out the sigma, the internal stresses, and that will turn out to be negative 14.6 KSI. Now we're done with the example, so we figure out what this bar really feels when it feels squeezed. So it expands, but it can't because of the supports at A and B. But I'll give you here some real-life examples and implications of thermal deformations. And if we're not paying attention to these, we'll have really serious problems in the structures and the systems we design. So if you walk around in huge buildings, like in airports or malls, you will find these like metal joints in the building. It's like as if someone with a knife came and cut the building and then tried to cover what they did. So it's actually on purpose. So in huge buildings, over lengthy parts of it, the temperature change will cause dramatic expansion and movement of the building. And if the building is huge or long, that will cause it to expand, and the midpoint in the building will feel kind of stretched between this side of the building and this side of the building. So if you don't do that, you have to design for it, and designing for it will cause increase in your cross sections beyond what's economical. So the idea is to just cut it in half, cut the building in two halves through expansion joint. That causes some issues when you deal with thermal comfort within the building or energy savings. So these expansion joints need to have good quality control during construction. Another example here is parking structures. So and just to give you an example here, that not all joints in buildings are expansion joints. So for example here, this is an expansion joint. This is a huge parking structure here. So we'll kind of the designer figured out I have to put thermal expansion in the middle of it. But there are other expansion joints here that we put not because of the thermal issue, but because of the structural difference between the two parts of the building. So if I look in this whole thing here is a different structural system and model than the ramps. And the deformation that can happen because of earthquake or the regular loads for this part and this part will be different, and their displacements will be different. So I have to account for that by just splitting them, not because of thermal, but because of the structural irregularity here, what we call. And then the other expansion joint we have is the fire separation for safety reasons between the evacuation shafts of any building and the building itself. So that's kind of a couple of real life examples to show you the real implications of thermal expansions. And if we don't pay attention to these, we either have to design for it, or we have to change our design to relieve ourselves from designing it and relieve the building from feeling any stresses because of thermal expansions or contractions. All right, thank you for watching and take care.